Today we're going to use logarithmic equations to help us solve equations that have logarithms in them. And we're going to apply our properties, which we should be fairly familiar with. We've been spending a couple of days expanding and condensing with our logarithmic properties. And now we're going to apply them to solving the equations. And here's the things that you need to do to solve equations. First, we need to use our logarithm properties to simplify the equation as much as possible. In fact, what we want to do is we want to try to get the equations to a point where there's one logarithm on the left side of the equals and there's one log on the right side of the equation at most. Once we've achieved this, then we're going to be dealing with one of two types of equations. The first equation is going to be a log equation that's really an exponential equation. And what happens here is after we use the properties, there is only a logarithm on one side of the equation. We rewrite the logarithm in its equivalent exponential form, we solve for x, and then we check for extraneous solutions, which means it's a solution that looks like it's perfectly good, but when we put it back into our equation, it doesn't work. And if you look at the bottom of your paper here, at the bottom it says, remember the domain rules for logarithms, log SP of n equals p, the n must also always be greater than 0. So as we look at this example here, log of x minus 3 plus log of x equals 1. We look for our properties here, and we're always looking to see, do we have a coefficient on any logarithms? And we do not have any coefficient on any logarithm. So the next thing that we look for is, do we have a plus or do we have a minus in here? We have a plus in our logarithm, so plus means that we can condense our logarithm down into log of x minus 3 multiplied by x equals 1. So we multiplied the two values on the left side of the equation, and now what we have left is we have one logarithm left in the equation. And because there's only one logarithm left in the equation, that means that we need to go back to our converting this to an exponential form. And the first thing that we need to also recognize to be able to convert to an exponential is that the base of a common log is 10. And when we convert here, what we're going to do is we're going to take the 10 and we're going to go up and around. So now what's going to happen is that we're going to have 10 to the first equals x minus 3 times x. Well, we can use distributive property over here on the right side of the equation. 10 to the first is simply 10, and we have x squared minus 3x. So it puts us here into a quadratic form, and oftentimes when we have a quadratic, we use factoring to solve. So we'll subtract 10 from both sides. And when we subtract 10 from both sides, we get 0 equals x squared minus 3x minus 10. And we'll factor. X and x, factors of 10 that combine to be 3 are 5 and 2, minus and plus. So finally then, to get our value, because ultimately what we're trying to do is we're trying to solve for x. So we want to take x minus 5 equals 0. X plus 2 equals 0, and we're going to add 5 to both sides. And we're going to subtract 2 from both sides. And now once we've completed this, once we've found the values for x, we need to check for extraneous solutions. So that means we need to take our answers and we need to go back into our original equation and we need to look and make sure that this part of the logarithm, oftentimes called the argument, it has to be positive. X has to be greater than 0. That value has to be greater than 0 for our domain. This value must be greater than 0. It has to be a positive value. So if we take our answer of 5 and we put that back in here, 5 minus 3 equals 2, and 2 is a positive number. We're good there. If we put 5 back in here, 5 is already positive, so we're good there. When we take our other answer of -2, -2 minus 3 is -5, and that value is negative, which means that it is going to be an extraneous solution. So the only answer to this problem is going to be x equals 5. The second type of logarithmic equation is one that's a true log equation. And what happens is, after we apply the properties, there ends up to be a logarithm on the left side of the equation, and there's a logarithm on the right side of the equation. And the steps that we follow then are we're going to cancel the logs. Secondly, we're going to solve for x. And thirdly, we're going to check for extraneous solutions. Don't forget that the domain rules still apply. But we'll deal with that here in the extraneous solutions. By the way, an extraneous solution means that it looks like a perfectly good answer. But when we put it back into our original equation, it doesn't work for us. It doesn't fit in the domain. Well, if we look at our example in this particular case, the first thing that we need to notice is that we have a number in front of our logarithm. And not only do we have a number in front of the logarithm over there on the left side, but we also have a number in front of the logarithm on the right side. And what happens is when we have a coefficient on the logarithm, we can rewrite that with an exponent. There's our power property of logarithms. So as I rewrite this, it's log base 3 of x minus log base 3 of 2 squared equals log base 3 of 3 cubed. And some of you won't even write down 2 squared. You'll go directly to the 2 squared is 4 and 3 cubed is 27, and I'm fine with that. I don't want to skip a step on this problem. So I'll do that in our next step. We get log base 3 of 4 equals log base 3 of 27. But we still have one more property to apply. Now that we've dealt with the power property, we've taken care of those coefficients in front of our logarithm, we have a minus sign. What does minus tell us to do? It tells us to divide. So we're going to get log base 3 of x divided by 4 equals log base 3 of 27. To solve it, that's what we're going to do. But our next step now, we've applied the properties. It's a true log equation. We have a logarithm on the left, we have a logarithm on the right. We can cancel the logs. They don't really cancel out, but for all intents and purposes, that works for people. And now we want to finish by solving for x. And we get x divided by 4 equals 27. And to finish, x divided by 4, our inverse operation says that we can multiply both sides by 4. And when we do, we get x equals, and 4 times 7 is 28, 4 times 2 is 8, 9, 10. Now, we look at this and we need to figure out, is this an extraneous solution? So once again, we need to go back into the original equation, and we need to make sure that this value, sometimes on the internet called the argument, has to be positive. 2 is already positive. We don't have to worry about that. And 3 is already positive. We don't have to worry about that. But when we put 108 back into the equation, 108 is greater than 0, which is the domain of the function. So 108 is a solution to our logarithmic equation. As we turn the page, we see that we have a natural logarithm in our next problem, but the properties, whether it's log or natural log, the ln, they still apply, and we need to follow our steps here. The first thing that we need to look at is, it says mark any equation that's an exponential equation first, And when we have an exponential equation, that means that we're not going to have a logarithm everywhere. But in this first particular problem here on the back, it seems that we have natural log, natural log, natural log, in all three parts of our equation. So this is not going to be an exponential. This is going to be a true logarithmic equation. And the first thing that we need to deal with is, do we have a coefficient? And we have a coefficient of 1/2. So we're going to make that, use our power property. This is going to become natural log of 25 to the 1/2 minus natural log of x equals natural log of 20. Some of you will be able to skip some steps here, but I recommend getting a few of them down because I find that people make more mistakes when they skip the steps. But the thing is, can we figure out what 25 to the 1/2 power is? And just as an aside, I want to say that 25 to the 1/2 power equals the square root of 25. Now, you can type it in. It's all numbers. So typing in 25 to the 1/2 is allowed. So 25 to the 1/2 equals square root of 25. And what's the square root of 25? 5. So we get natural log of 5 minus natural log of x equals natural log of 20. And we still need to apply the properties. We apply the properties. We want to turn this equation into one logarithm on one side of the equals and one logarithm on the other side of the equals. We once again have a minus sign. And what does minus tell us to do when we're dealing with logarithms? It tells us to divide. So it's going to be natural log of 5 divided by x equals natural log of 20. Now that we have a logarithm on the left, a logarithm on the right, a single logarithm on each side, we can cancel the logs, and we can finish by solving. And it's 5 times x equals 20. Gonna do a couple more steps than maybe you need to. The first one being, let's multiply both sides by x. When we multiply both sides by x, we get 5 equals 20x. And then lastly, 20 times x. When we divide both sides by 20, we end up with x equals 1/4. 5 divided by 20 is 1/4. Once we get this value, we need to go back and check for extraneous solutions. We're going to go back into the original equation. When we go back into the original equation, the nice part is that 25 is already positive. This value here must be positive, and 20 also must be positive. When we look at our solution of 1/4, is 1/4 positive? Yes. So we do not have any extraneous solutions in this problem.
So if it's negative?
You can have a negative answer. It's when you put it back into the problem, it can't be negative. That's the only time. I mean, you can end up with x equals -2, and it can be an answer. However, more likely would you get a negative solution to be extraneous. So as we look at problem number 2, again, the directions say mark any equations that are exponential equations. And the biggest thing to look for when we're looking at these for something to be exponential is that there's at least one value that doesn't have a logarithm with it. And in this case, there's 2 values that don't have a logarithm with it. So this one is going to be an exponential equation. It's like the very first example that we did on the front page of our notes. And what we need to do is we need to isolate the logarithm. We want to get at least one logarithm on each side, but in this case, get the natural log of 2x plus 1 equals 2. So now we have one logarithm on the left side. We don't have any logarithm on the right side. What's the base of a natural logarithm? Somebody said it. It's e. And because it's an exponential, we need to convert this into exponential format. That means we're going to take this value of e, and we're going to go up and around. Remember that a logarithm is another way of writing an exponent. Whatever this logarithm equals is an exponent. So when we convert, this is going to be e squared, there's the exponent, equals 2x plus 1. And then when we solve this here, I'm going to subtract 1 from both sides, and we get e squared minus 1 equals 2x. And then it's 2 times x, so we need to divide both sides by 2. And we get x equals e squared minus 1 divided by 2.
I don't see where you got that. Where did you put that E? No, I get you just trying to plug that E in, but like, where did you put the E?
I started with the e. That's the basic. Natural log of e.
Yeah.
Went up and around. Whatever the logarithm equals is the exponent. That's where it's 2. E squared.
You took that 10 meters.
Yep.
Why did you bring the drop all the way to the 6-point round?
I'm weird.
Went under the 2.
That's what we said the other day.
Problem number 3. Again, first thing that we should do is we should check. Do we think this is going to be an exponential equation? Well, when we look at it, we have log base 8 of x plus 10, we have log base 8 of x minus 1, we have log base 8 of 12. Not going to be exponential. There's there's a logarithm on all of these terms. So when we simplify this here, there's no coefficients on any of the logarithms. So the first part that we're going to deal with is the fact that we have a minus sign in there. And what operation does minus tell us to do when we apply it to the logs? It tells us to divide. So we're going to get log base 8 of x plus 10 divided by x minus 1 equals log base 8 of 12. Once we apply the logarithms, the logarithm properties, we ended up with one logarithm on the left and one logarithm on the right. And because of that, our log base 8s are going to cancel out. And now we have x plus 10 divided by x minus 1 equals 12. When we want to solve, we can multiply both sides of this equation by x minus 1. So the x minus 1's cancel out over here on the left side. And we're left with x plus 10 equals 12 times x minus 1. And some of you distributed already, and I know. I just personally do not like to skip steps if I can help it. So we do need to distribute. We're going to distribute the 12. And we end up with x plus 10 equals 12x minus 12. And then we can solve. Solve it the way your Algebra 1 teacher taught you to solve it. I tend to move my letter to the left. It won't make any difference here. We get negative 11x equals negative 22. And then when we divide both sides by negative 11, we end up then with x equals 2. But again, we have to be conscious of extraneous solutions. An extraneous solution means that it looks like a perfectly good answer, but when we put it back into the problem, it doesn't work for us back in the problem. We're going to go back to the original equation, and we're going to put that value back in to x plus 10. We're going to put that value back into x minus 1. We don't have to put it back into 12. 12 is a constant. It's already positive. It's 2. 2 plus 10 is 12. 12 is positive. 2 minus 1 is 1. 1 is positive. It meets the requirements for our domain, so therefore this is a legitimate answer to our problem. No extraneous solutions. So the biggest issue on these problems is just deciding, do we have an exponential equation or do we have a true logarithmic equation? As you look at this one, what's your gut instinct? Not true log, which is also known as an exponential. And it's true that it's not true log because there's no logarithm with a 0. There's a logarithm with the 4x minus 1. There's a logarithm with the 2x, but there isn't a logarithm with the 0. So it's going to be an exponential. We look and see if we can apply the power property, and we don't have that. But this time, finally, we have something a little bit different. We have a plus in the problem, and what does plus tell us to do? It tells us to multiply. So we get log base 5 of 4x minus 1 times 2x equals 0. I'm going to simplify a little bit more, and you don't have to do it at this point, but at some point you're going to have to distribute. So it's 2x times 4x is 8x squared. 2x times negative 1 is negative 2x equals 0. And again, a logarithm is another way of writing an exponent. So what's our base on our logarithm? Our base is 5. But whatever the logarithm equals is what our exponent is. So what's our exponent in this problem? There's the 0. It's going to be equal 8x squared minus 2x. So if we don't know what 5 to the 0 is, we can go over to the calculator and we can type it in. 5 to the 0 is 1. So we've got 1. So 1 equals 8x squared minus 2x. And then we're going to subtract 1 from both sides. So we have 0 equals 8x squared minus 2x minus 1. And we're going to have to factor. So on this particular problem, we haven't seen slide divide for a while. So let's factor. And we're going to take that 8 and we're going to slide it over. And we end up with x squared minus 2x minus 8. And we can factor. It's easier to factor with x squared than it is with 8x squared. If you like the split the middle method, feel free to do the split the middle method. But the factors of 8 are 4 and 2. And then it's going to be negative 4 and positive 2. Don't forget, this method's called slide divide. So we're going to have to divide by what we slide. So divide there. But we're left with x minus 1/2 when we simplify that. And we're left with x plus 1/4 when we simplify 2/8. And I don't think that we really need to spend the time doing the bottoms up here, because our goal is, what does x equal? And in this format, hopefully you can tell me that x equals 1/2, and that x equals negative 1/4. And then what that means here, by the way, I took x minus 1/2 and set it equal to 0 to solve. X plus 1/4 and set it equal to 0 to solve. And now what we need to do is we need to go back and check for extraneous solutions. So we've got x equals 1/2. If we put 1/2 back into this equation at the 4x minus 1, that value has to be positive. Based on the domain of a function, that value has to be greater than 0. So 4 times a half is 2. 2 minus 1 is 1. Is 1 positive? Yes. And over here, 2 times 1/2 is 1. Is 1 positive? Yes. If we try the negative 1/4, well, 4 times negative 1/4 is negative 1, minus 1 is negative 2, and there we hear it. Negative 2, not positive. That means that x equals negative 1/4 is extraneous.
Without whatever stays different than e.
Number 5. Remember, when we're working with these problems, what we want to look at is this an exponential or is this a true logarithmic problem? And we have a minus 2 in the problem that doesn't have a logarithm in front of it, which means that this is going to be an exponential. So when we're working with this problem, what we want to do is we want to rearrange it in a little bit better format so that we have the logarithms on one side of the equation and everything else on the other. So when I rewrite this problem, I'm going to subtract log of x plus 1 from both sides. And even though I'm not going to show my work on this, we end up with log of x squared minus 1 minus log of x plus 1. And I'm going to move this negative 2. It doesn't fit up there, but we're going to move that negative 2 to the other side, and when we move it to the other side, it's going to become positive 2. So we have the logarithms all on the same side of the equation. We have a minus in it, and we can use the properties of logarithms. Minus tells us that we can use the quotient property, which says that this is going to be log of x squared minus 1 divided by x plus 1 equals 2. Well, it's an exponential, so we need to write this as an exponential, and the other thing that we need to know is that there's no base written on that logarithm, so we're working with the common logarithm, and a common logarithm means base of 10. When we convert this to an exponential, we take this 10, and we're going to go up and around. So this is going to be 10 squared, 10 squared, equals x squared minus 1 divided by x plus 1. One comment, again, that you've heard earlier on the video is that a logarithm is another way of writing an exponent. Whatever the logarithm equals is the exponent. So notice that 2 is the exponent in this problem. There's a couple of ways to do this problem, but I'll stick with the way that I have here, and that is that 10 squared is 100, and that equals x squared minus 1 divided by x plus 1. Well, what we're going to do is we're going to multiply both sides of this equation by x plus 1. And when we multiply both sides of this equation by x plus 1, we get rid of a fraction. And it's really going to be x plus 1 in parentheses times 100 equals x squared minus 1. And we're going to distribute. So we're going to get 100x plus 100 when we distribute equals x squared minus 1. But we want to write this in a format where we can actually factor this problem. So let's subtract 100x from both sides. And not only that, but let's subtract 100 from both sides. And what we end up with is 0 equals x squared minus 100x minus 101. Negative 1, negative 100 combined together. And some people look at that and go, well, we can't factor that, but we can. X squared is x times x. 101 times 1 will give us 101. And if we take negative 101 plus 1, and then lastly, we take x minus 101, and we set it equal to 0. When x plus 1, set it equal to 0, which means that x equals positive 101, or x equals negative 1. but we need to go back and check for extraneous solutions. We go back to the original problem, and in the original problem, the x squared minus 1, that has to be positive. Domain, that value has to be greater than 0. X plus 1, that value has to be positive. It has to be greater than 0 to fall into our domain category. When we put 101 in there, even though I don't know what 101 squared is, I know that 101 times 101 minus 1 is a positive value. And over here on the right side, 101 plus 1 is 102. Both of those values are positive. Negative 1 here is our other solution to this equation. And negative 1 squared is 1. 1 minus 1 is 0. 0 is not positive. It doesn't have a sign of either positive or negative. So our negative 1 value here is an extraneous solution. If I go back to the beginning here, negative 1 plus 1 here is also 0. Again, 0 is not positive. Last one. We need to determine whether this is an exponential or a true logarithmic equation. And the way that we determine that is we look and see, does every term in the equation have a logarithm in it? And the answer is no. Not every value in here has a logarithm with it. So when we go back here, we can say that this is an exponential type of logarithm equation. So the first thing that we notice is that there's a 3 in front of the logarithm. And when there's a 3 in front of the logarithm, we can rewrite this log as log base 2 of x cubed. We also have a 2 in front of this logarithm, and it is also going to use our power property, which says log base 2 of 5x squared equals 2. Now that was helpful here. The thing that I need to warn you about is that 5x squared means 5x times 5x, and 5 times 5 is 25, and x times x is x squared. So if we go back and rewrite that equation, it's going to be log base 2 of x cubed minus log base 2 of 25x squared equals 2. Well, we still haven't condensed it down into a single logarithm there on the left side. So we see that we have a minus in this problem. And what happens then is we can condense it into a single logarithm of x cubed divided by 25x squared. And then we're going to convert it into an exponential. So it becomes 2 squared equals x cubed divided by 25x squared. If you prefer, go up and around. So as we simplify that a little bit more, we end up with 4 equals x cubed divided by 25x squared. And let's get rid of the fraction by multiplying both sides of the equation by 25x squared. So we multiply both sides by 25x squared. And the 25x squared cancel out over here. And on the left side, we're left with 100x squared equals x cubed. Well, we're going to have to factor again, and we're going to move the 100x squared to the other side over here with the x cubed. And we have 0 equals x cubed minus 100x squared. If we factor out a greatest common factor, our greatest common factor is x squared times x minus 100. So when we solve this, we've got x squared equals 0 and x minus 100 equals 0. Well, when we take the square root of both sides, we still get x equals 0. And over here, when we add 100 to both sides, we get x equals 100. And we need to check for extraneous solutions after we get those values. So we go back to the original equation and the value that we're looking at. That x must be positive. Our domain has to be greater than 0. 5x has to be greater than 0. It has to be positive. Well, one of our answers that we ended up with was 0. 0 is not positive, which means that 0 is extraneous. But let's check our value of 100 for x. Well, 100 is positive. 5 times 100 is 500. It also is positive. So our solution to this problem is x equals 100.